Hi, my name is Aditya, and I'm going to tell you about our web search and text mining project, which is the adaptive learning-based approach to dual-branch graph convolutional networks on imbalanced node representations. Classifying data with machine learning classifiers can be difficult when training on imbalanced datasets. In some severe cases where minority class to majority class ratios are 1 to 10 or even 1 to 100, training on this data risks subpar classification performance due to fewer observations from the minority and oftentimes more important classes. Resampling has been shown to reduce class imbalances through artificially populating minority classes or decreasing majority class representation. Resampling with graph networks, however, is difficult to carry out as network observations are interconnected and not independent. In our project, we wanted to devise a model architecture that is resilient to class imbalances. For our baseline model architecture, we used the dual-branch GCN proposed by Wang and Chen. In this model, two branches carry out the GCN training on two versions of the input network. One branch trains on the original unmodified graph, and the other branch trains on a reconstructed graph built using the k-nearest neighbors algorithm to connect similar nodes based on their features. Using the bilateral branch network architecture proposed by Zhu et al. As inspiration, we wanted to design a GCN architecture using the same concept. In this model, we build a similar double branch classifier where one branch processes the original graph similarly seen in Wang and Chen's implementation. However, we wanted to use the technique seen in Zhu et al.'s architecture, where instead of reconstructing the graph, we sample nodes probabilistically and inversely proportional to the number of representations of the class to which they belong. In this implementation, we modify parameter alpha, which dictates the amount of influence the minority classes have in the current batch sample in the reverse sampling branch. As the number of epochs increases, the influence of minority classes also increase. Since the original bilateral branch network was configured as a convolutional neural network, the main challenge we faced was figuring out the best way to adapt the reverse sampling technique for graph network data. Since observations in network data are not independent, we chose to include any edges between resampled nodes that were present in the original graph, and emitting edges between unsampled nodes. In our model, we also use cumulative learning backpropagation over both branches. We decided to use the DBLP, CiteSeer, and PubMed citation network datasets. These datasets were previously analyzed in prior studies with branch network designs and held great utility in studying imbalanced networks. Each node in these datasets represented a research paper, and each edge between nodes represents a citation link. Nodes were categorized based on their topics of their associated paper. Another big motivator behind using these datasets was that these libraries came preloaded with PyTorch geometrics library, including information like node-wise ground truth labels and edge indices. Here are our model hyperparameters. In both cases, we use multi-layer models and modified weight decay, learning rate, and weight dropout rate to discourage overfitting and increase generalizability. These trials were conducted using Google Colab and JupyterLab with CPU and GPU hardware. Models were trained over 50 epochs and evaluated based on their accuracy metrics. For the baseline DGCN model, the optimal learning rate was 0.001, whereas for our implementation, the BGCN, the learning rate was 0.01 to return the optimal results. Here are our accuracy results comparing the baseline model with our implementation. As you can see, our model performed better than the baseline model using the DBLP and CiteSeer datasets, but saw a decrease in performance when training on the PubMed dataset in comparison. Here are the training accuracy and loss plots for our model implementation using the DBLP dataset. Here are the results for our model using the PubMed dataset. Finally, here are the training accuracy and loss curves for our model using the Sightseer network dataset. Our proposed model outperforms the baseline DGCN model for the DBLP and Sightseer datasets. However, when comparing performance using the PubMed dataset, the accuracy of our proposed model is lower than the baseline performance. One key observation that was made was that across all three datasets, our model's performance peaked roughly halfway into the training process. We believe that this is caused by our alpha parameter, which determines the reverse sampling rate and ultimately regulates the amount of influence the minority classes have during training. Since the alpha function is exponential with respect to the number of epochs, we believe that the loss values peak when alpha approaches 0.5 for this reason. Future works include analyzing optimal functions for alpha and testing out a variety of linear and other nonlinear functions. Additionally, another avenue of study could involve deeper research into Wang and Chen's dual-branch GCN model and determining optimal clustering algorithms and parameters that outperform the baseline KNN graph reconstruction approach.